Water kills people who don't drink it, and it kills people who drink too much of it. Water wears down rock and is softer than any stone. Water is 800 times heavier than air and still climbs to the tops of trees 30 meters tall, defying common sense. Water is the only substance on Earth that we drink, wash with, breathe as vapor, and walk on in winter. And after 1,000 years of study, science still cannot fully explain how it works. Scientists have discovered black holes, captured colliding galaxies on camera, and created materials that don't exist in nature. But water, the simplest molecule of 3 atoms, still guards secrets that no computer and no theory has been able to crack. More than 60 of its properties are officially recognized as anomalous, violating the laws of physics and chemistry. Not one, not two, more than 60. This isn't a colorful metaphor, it's a statement of fact acknowledged by mainstream science worldwide. If you're watching this thinking that water is just a transparent liquid you pour into a glass, prepare for the next hour to change your understanding of the most ordinary substance in the world. Because behind that ordinariness lies something that still makes scientists uncomfortable. They have been studying water for 4,000 years and still don't have answers to the most basic questions. Let's start at the beginning, with how humanity spent millennia being completely wrong about water and completely certain it was right. Around 600 years before the Common Era, the Greek philosopher Thales of Miletus declared water to be the primordial substance of all existence. Not fire, not air, not earth. Water. Everything that exists is born from water and returns to it. Thales was one of the sharpest minds of his time, and his idea seemed logical. Water is everywhere, it changes form, it generates life. He watched the Nile flood in spring and bring forth harvests, and drew his conclusions. Later, Aristotle complicated the picture. For him, water became one of 4 elements alongside fire, air, and earth. That framework held for nearly 2,000 years. 2 millennia, people looked at water and thought, well, yes, one of the elements, all clear. Nothing mysterious here. In medieval Europe, alchemists tried to turn water into gold by dissolving everything they could find in it. Water fascinated them precisely because of its ability to dissolve. It seemed like an almost magical substance, capable of absorbing the properties of other things. They were closer to the truth than they realized, but for completely different reasons, which we'll get to shortly. The turning point came in the 18th century. In 1783, French chemist Antoine Lavoisier ran an experiment that shattered 2,000 years of certainty. He passed an electric current through water and broke it down into 2 gases, hydrogen and oxygen. Water turned out to be not an element, not a primal substance. It was a compound, a simple chemical compound of 2 of the most common elements. The scientific world breathed a collective sigh of relief. Now everything was clear. Water is hydrogen plus oxygen. 2 atoms of hydrogen, 1 atom of oxygen, 3 atoms, the simplest molecule, solved. But within a few decades, something strange began. Scientists started noticing that water didn't behave the way it should. Not slightly wrong, fundamentally wrong. It was breaking one rule after another. Every time it seemed like they had finally understood it, it threw up a new puzzle. Italian chemist Amedeo Avogadro wrote down the familiar formula in 1821. 2 atoms of hydrogen to 1 atom of oxygen. It seemed like the final word. But by the late 19th century, something inconvenient had emerged. The molecular mass of liquid water, measured through its solutions, turned out to be higher than the simple formula suggested. As though the molecules didn't want to stay alone. They clung to each other and moved in groups. The formula was right, but water didn't live by it. In 1932, a discovery was made that left physicists speechless for years. American chemist Harold Urey discovered heavy water, a substance with the same combination of atoms, but with different hydrogen atoms. In this water, both hydrogen atoms are replaced by deuterium, a heavy isotope whose nucleus contains not just a proton, but also a neutron. Chemically the same, visually the same, but a completely different substance with completely different properties. It boils at a different temperature, freezes differently, and living organisms die in it. Academician Igor Petrianov-Sokolov, founder of the journal Chemistry and Life, wrote of this discovery. There is no such thing as ordinary water anywhere. It is always extraordinary. In any glass of water, there is a mixture of molecules with different isotopic compositions. If you count all possible combinations of hydrogen and oxygen isotopes, you get more than 40 varieties of water sharing the same simple formula. Most of them are radioactive, some exist only in laboratory conditions, but they are all water. A family of molecules with a common name and completely different personalities. No longer a simple 3-atom compound, a whole world behind a plain exterior. But the strangest thing isn't the isotopes. The strangest thing is how an ordinary plain water molecule, the kind that comes out of your tap, actually behaves. This is where the laws of physics start breaking down. A water molecule looks simple. 2 hydrogen atoms attached to 1 oxygen atom at an angle of roughly 104 degrees. A small angle, an asymmetric structure. If the atoms were arranged in a straight line, water would be a completely different substance. inert, indifferent, and almost certainly incapable of supporting life. That angle is what makes the water molecule polar. One end of the molecule is slightly positive, where the hydrogens are. The other is slightly negative, where the oxygen is. A water molecule is a tiny magnet, a small dipole. In itself, that's not surprising. Many molecules are polar. But water is a special case. That angle, that asymmetry, produces an effect physicists call the hydrogen bond. Each water molecule can simultaneously form 4 such bonds with neighboring molecules. 2 through its hydrogen atoms and 2 through its oxygen atom. 4. Most molecules have 1 or 2 such bonds. Water has 4. Picture a busy city bar. An average customer knows 2 or 3 neighbors, exchanges a few words, and that's it. Now imagine every person in the bar is gripping 4 people's hands simultaneously, and each of those people is gripping 4 more. The entire crowd becomes one interconnected living network. That's how liquid water works, not a chaos of individual molecules, a constantly reshaping web of connections. This web doesn't freeze in place. Hydrogen bonds last for a trillionth of a second, snap apart instantly, and immediately reform with a new neighbor. Water is continuous restructuring, an endless molecular dance of partners separating and rejoining faster than light can blink. It's precisely this peculiarity that makes water disobedient. When chemists try to predict water's properties by looking at its nearest relatives on the periodic table, hydrogen sulfide, hydrogen selenide, hydrogen telluride, they get a very clear picture. By every law of chemistry, water should be a gas at room temperature. It should boil at around -80 degrees Celsius. It should freeze at around -100, no liquid state under the conditions we experience. That number deserves to be said again separately because it upends our intuitive picture of the world. If water were a normal substance, a dutiful student of the laws of chemistry, there would be no rivers, no oceans, no rain on Earth. There would be no liquid water at all. There would be a colorless gas we breathed without ever suspecting that if it were slightly heavier, it would become the foundation of life. Water boils at 100 degrees Celsius, 180 degrees higher than the laws of chemistry predict. That's not a small margin of error. It's a colossal deviation. It's explained entirely by those hydrogen bonds, which prevent the molecules from flying apart and require an enormous input of energy to break. But hydrogen bonds are only the beginning of the explanation. Even knowing about them, scientists still cannot predict all of water's properties. Computer models can only approximate them. Something in water remains beyond the reach of any theory. And this is where the anomalies begin. The first one, the one you've probably heard of, but probably never fully thought through. Ice floats on water. It seems so obvious that it stopped being surprising a long time ago. Ice in a glass sits at the top, icebergs stick up above the waves, rivers freeze over from the surface down. So what? That's how it's always been. Now imagine that wasn't the case. For every other substance in the universe, the solid state is denser than the liquid. A chunk of solid iron sinks in molten iron. A chunk of solid lead sinks in liquid lead. A chunk of solid sulfur sinks in molten sulfur. This is a fundamental principle. When a substance crystallizes, it becomes more compact. Its molecules pack more tightly. Its density increases. That's how everything works, except water. When water freezes, its molecules arrange themselves into a special lattice, hexagonal, 6-sided, the same lace you see in snowflakes. Beautiful, but with a secret. It's loose. In this lattice, there is significantly more empty space between molecules than in liquid water. The molecules are held at a set distance from each other by those 4 hydrogen bonds, each of which requires a specific angle and a specific distance. The density of ice is about 9/10 of liquid water's density. About 11% of the volume of any piece of ice is empty space. Empty space that keeps it floating. If the molecules in ice packed as tightly as in most solid substances, ice would be roughly twice as dense as liquid water. It would sink, instantly and inevitably. What would that mean for life? In winter, when temperatures drop below zero, the surfaces of rivers and lakes would begin to freeze, as they do now. But the ice would sink to the bottom, layer by layer, year by year. Rivers and lakes would freeze solid, from the bottom to the surface. Even a brief summer wouldn't be enough to melt the ice at the bottom, insulated by new layers of water above it. Freshwater bodies in temperate latitudes would become permanent permafrost with a thin summer film of water on top. The first living organisms that arose in water couldn't have survived a single winter. Ice is a protective layer. When a river freezes over from the top, that crust acts like a blanket. It insulates the water beneath it from further cooling. Under the ice, liquid water remains at temperatures between 0 and 4 degrees. That's where fish, frogs, and aquatic insects overwinter. That's where the biochemical processes continue that will restart life at full power come spring. Floating ice is not one of nature's quirks. It is its safety net. Scientists from the Stanford Synchrotron Radiation Light Source led by Anders Nilsson conducted research using powerful X-ray radiation from synchrotrons in Japan and the United States. They discovered that water molecules in their liquid state exist in 2 types of structure simultaneously, ordered clusters of roughly 100 molecules with a near crystalline arrangement, and a disordered medium surrounding them. This finding was published in the Proceedings of the National Academy of Sciences. Nielsen described it through the image of a nightclub. Some molecules sit at tables in an orderly arrangement, others move continuously on the dance floor. Raising the temperature makes people get up from the tables and join the dancers. Cooling sends them back. At any given moment, both types of structure coexist. This is what explains water's anomalous density behavior. As it cools, the more ordered and looser structures begin to dominate and water becomes less dense. Up to a certain point, this effect overrides the ordinary compression from cooling, which is why water's maximum density is not at 0 degrees, as one might expect, but at 4. At 4 degrees Celsius, water is at its heaviest. It is that layer that sinks to the bottom of winter lakes and creates a zone where life can continue even through the most brutal frosts. 4 degrees is the temperature at which water keeps life alive. The density anomaly is only one side of the story, because water doesn't only know how to preserve life, it also knows how to preserve something else entirely, something without which our planet's climate would long since have turned into either a desert or a glacier. And it comes down to a property of water that seems completely mundane, but is in fact one of the most extraordinary in nature. It has to do with heat, specifically how water holds it. Pick up a cup of hot tea and hold it for a minute. It burns. Now place a piece of heated metal of the same mass and the same temperature next to it and step back. The metal will cool down several times faster, the water will hold its heat long after the metal has reached room temperature. This seems like a trivial everyday observation. But this property of water is one of the reasons London doesn't freeze to death every winter and Moscow doesn't turn into a desert every summer. Physicists call this heat capacity. Water's heat capacity is anomalously high, higher than almost any other common substance. To heat water by 1 degree, you need 4 times as much energy as for the same amount of air, and 9 times as much as for iron. Where does this capacity come from? Again, from hydrogen bonds, but now working in a different mode. When you transfer heat to water, a significant portion of it doesn't go into accelerating the molecules. It goes into breaking the bonds between them. The molecules absorb the energy by breaking one contact and establishing another. Water doesn't rush to heat up. It's busy reorganizing internally. And in the same way, when cooling, it releases its stored energy slowly and reluctantly. Imagine a warehouse filled with an enormous number of springs, tightly interwoven with each other. To heat this warehouse, you need not only to accelerate the boxes on the shelves, but to stretch thousands of springs, pulling the boxes apart. Energy goes into the springs and is stored there. When the warehouse begins to cool, the springs slowly compress back, releasing their stored heat. Water is that warehouse, with a countless number of spring-like bonds acting as a thermal battery. The consequences of this property for life on the planet are immense. The world's oceans cover more than 70% of Earth's surface. They absorb solar heat in summer and slowly release it in winter. That is why coastal cities have significantly milder climates than cities deep in the interior of continents. London sits at the same latitude as Moscow, but its climate is fundamentally different, because the Atlantic is nearby, and it still remembers summer well into December. Take the extreme case. If the ocean's heat capacity were the same as soil or rock, daily temperature swings on Earth's surface would be tens of degrees, heat in the day capable of killing most living things, frost at night incompatible with life. Not a gradual change of seasons, a daily catastrophe. Through its heat capacity, water turns the Earth into a thermostat, a device that keeps temperature within livable bounds. This effect shows up particularly vividly in another phenomenon, the latent heat of evaporation. When water transitions from liquid to vapor, it absorbs an enormous amount of heat, and its temperature doesn't change by a single degree. All the energy goes into breaking the bonds between molecules rather than heating them. Water's latent heat of evaporation is roughly 7 times higher than that of most other liquids of the same mass. This is what protects you from overheating in the heat. When you sweat, you don't just get wet. Every drop that evaporates carries away a massive amount of thermal energy from the surface of your skin, cooling you from within. A running engine is cooled by water for the same reason. Rain clouds form and dissipate, moving heat from the equator toward the poles, and underlying all of it is the same property. Water absorbs heat without raising its temperature, like a sponge that soaks up water without changing its outward appearance. One of the most striking examples of this effect is the human body. We are roughly 60% water, and that is what makes us stable against temperature swings. Our bodies are thermostats with water cooling. Without water, under the same thermal load, our tissues would overheat within minutes. Water's heat capacity is one of the ways it violates ordinary logic. There is another anomaly connected to its physical behavior, one that's easy to overlook, because we watch it happen every winter and have become so used to it that we stopped asking questions. Water expands when it freezes. Most people know this, at least because they've seen burst pipes or bottles that were left outside in the cold. But few have ever really thought about how non-trivial this expansion is and the scale at which it operates in nature. When water turns into ice, its volume increases by about 9%. 9% seems small at first glance, But the pressure this generates can exceed thousands of atmospheres. Thousands. This pressure can burst cast iron pipes, crumble granite, split mountains. That is exactly what happens in the mountains. Every winter, water seeps into cracks in rock. At night, the temperature drops below zero, the water freezes and expands, widening the crack slightly. Then day. Then night again. Then again. Year after year, water cuts rock apart. Without saws, without explosives. Geologists call this frost weathering. This process is what creates scree slopes, rocky wastelands, and the sharp peaks of high mountains. As it expands, water sculpts the planet's relief. In soil, the same thing happens, slower and on a larger scale. Water in the soil's pores freezes and lifts the upper layer. In spring, it melts and the layer settles. This cycle mixes the soil, breaks up compacted clumps, and brings nutrients to the surface. Soil freezing isn't destruction, it's renewal. Water works as a plow that nobody sees. In living cells, the same mechanics apply, but with the opposite sign. This is exactly why freezing destroys the cells of most organisms. The water inside the cell freezes, expands, and tears the cell membrane from within. The cell doesn't die from cold as such, it dies from the pressure of expanding ice. Some living creatures have evolved ways to fight this. Arctic frogs synthesize special compounds that prevent water inside their cells from forming crystals. Some fish produce antifreeze proteins that stop ice from growing. Biological workarounds to a physical anomaly that remains itself regardless of any tricks. Expansion upon freezing violates one of thermodynamics' universal rules. When substances cool, their molecules slow down and pull closer together. The space between them decreases, volume decreases, density increases. An iron law, which water violates as calmly as it violates all the others. The reason, again, is the crystalline lattice. Upon crystallization, water molecules arrange themselves into hexagonal rings. 6 molecules per ring. Beautiful, symmetrical, and wasteful with space. At the center of each ring is emptiness. The molecules are held at a fixed distance from each other, dictated by the geometry of their bonds. If they tried to get closer, the angle would break and the structure would collapse. So ice is forced to take up more space than liquid water. It has no choice. Order in water means looseness. Disorder means density, the complete opposite of how most substances work. This is a good place to stop and truly think about what a hydrogen bond is, because it isn't just a technical term that explains a couple of physical anomalies. It is one of the subtlest and most powerful forces in the chemistry of living nature, and simultaneously one of the weakest forces at the level of individual molecules. A hydrogen bond is roughly 20 times weaker than an ordinary chemical bond between atoms. It is broken by thermal motion in literally a trillionth of a second. One water molecule forms a bond, immediately breaks it, and forms a new one with a different neighbor. Continuous and lightning-fast switching of partners. But what is weak for a single bond becomes unbreakable when there are billions upon billions of bonds. The network of hydrogen bonds in water is a fabric woven from the finest threads. Each thread snaps at the slightest effort, but the fabric as a whole is strong, elastic, and flexible. It holds its shape and yet flows. It is this network that gives water the surface tension sufficient for a water strider to run across a pond. It is this network that pulls water up through the finest capillaries of plants against gravity, delivering nutrients to heights of dozens of meters. The hydrogen bond is not just physics, it is the foundation of biology. The double helix of DNA is held together by hydrogen bonds between base pairs. Proteins fold into their working shapes because of them, and unfold, losing their function when those bonds break. Viruses use hydrogen bonds to attach to host cells. Antibodies recognize foreign molecules through those same mechanisms. The hydrogen bond is the language in which the molecules of living matter speak to each other. And in this conversation, water isn't just a solvent in which life happens. It's a participant. It's part of the molecular dialogue. Physicist Philip Ball, author of a biography of water, puts it this way. Water doesn't simply fill the space around life's molecules. It actively participates in their functioning. When an enzyme works, the water around it reorganizes in a specific way, helping substrate molecules find the right position. When a protein folds, water pushes the hydrophobic sections inward, forming the working structure. Water is not a passive medium, it is a co-participant in biochemistry. And here arises a question that has long troubled scientists. How well do we actually understand the structure of water? The answer is sobering. We know the formula, we know the main properties, but the structure of liquid water at the molecular level is still the subject of heated debate. One reason, liquid water has no fixed structure. Unlike ice with its regular lattice or vapor with its free molecules, liquid water is something in between, and constantly changing. Ordered clusters of molecules exist, but live for infinitesimal fractions of a second before scattering and reforming. Capturing this, even with the most sophisticated instruments, is extraordinarily difficult. In 2014, Swedish scientists from Stockholm University proposed a model according to which liquid water consists of 2 alternating structures with different densities, something like 2 liquids mixed into one. This idea is still being debated in the scientific community, and has received neither definitive confirmation nor refutation. It sounds strange. We have computers capable of modeling the collision of galaxies. We have accelerators that can peer inside a proton. But the structure of a glass of water sitting on a table is an open scientific question without an answer. Perhaps the reason is that water is too alive, too dynamic, too continuously changing. The tools that work well with static structures can't keep pace with water. It is always one step ahead. If you think water's anomalies end with its behavior under ordinary conditions, there is something even more unexpected ahead. Because change the pressure, and water begins to behave in ways that defy every physical intuition. Compress most gases under high pressure, they condense into a liquid. Logical, compress most liquids, they turn solid. Pressure pushes molecules together and they form a crystal. Also logical. Water once again does something different. Under certain conditions, when pressure rises sharply, ice melts, not heats up, melts under pressure. High pressure destroys the loose crystalline lattice of ice, pushing molecules together so tightly that the disordered liquid state with its higher density becomes more favorable. The harder you press on ice, the lower its melting point drops. For a long time, this effect was considered the main explanation for why a skate blade glides on ice. The pressure from the blade supposedly melts a thin layer of ice beneath it, and the skater glides on water. A beautiful explanation that graced physics textbooks for decades. Calculations, however, showed that at typical blade pressures and temperatures of 10 to 15 degrees below zero, this effect is far too small. Pressure does melt ice, but only under far more extreme conditions. The real reason for skating's glide is still being discussed in scientific papers. According to the latest data, there is always a thin, quasi-liquid layer on the surface of ice, a result of surface disorder among molecules that have no neighbors above them to bond with. A textbook example of a confident explanation that held for centuries and turned out to be wrong. Here, another inverted logic of water under pressure emerges. When you dissolve gases in water, carbon dioxide in sparkling water, for instance, pressure helps. More pressure, more dissolved gas. Standard physics, but water has dissolved gases that behave in non-standard ways. As temperature rises, their solubility falls rather than rises. Fish in warm water suffer from oxygen deprivation precisely because warm water holds oxygen less well, a direct consequence of the same molecular architecture that makes water boil where it shouldn't. Water under pressure delivers one more surprise, a thoroughly exotic one. At extremely high pressures, in the millions of atmospheres found inside giant planets, water stops being a familiar liquid and becomes a supersonic state. Oxygen atoms form a solid crystalline lattice, while protons, the nuclei of hydrogen atoms, move freely through it. Simultaneously solid and liquid, simultaneously a crystal and a conductor. Scientists call this hot ice. Its existence was confirmed in laboratory conditions in 2017. It is believed this is exactly the state water exists in within the interiors of Uranus and Neptune, billions of kilometers from here. The planets we see in the sky as bluish-green spots through a telescope may have at their cores not unmelted metal, but something unimaginable. Hot ice made of water that conducts electricity. This may be what generates their magnetic fields. That still remains to be proven. And here, at the edge of understanding, between hot ice inside icy planets and a thin water film beneath a skate blade, between DNA molecules and the ocean's thermal memory, a question begins to sound that is impossible to ignore. All of this is too precise, too conveniently arranged, too necessary. Each water anomaly, taken on its own, looks like a strange physical curiosity. But together they form something else, a list of properties without any single one of which life on Earth would either be impossible or fundamentally different. Is this coincidence, or does something larger lie behind it? And where did all this water come from on a planet that formed from a scorching cloud of gas and dust around a young star? The question of what accounts for this precision has haunted scientists for a long time. Because when you start listing water's properties one by one and realize that each of them works in exactly the direction life requires, an uncomfortable feeling arises, scientifically uncomfortable. Like looking at a lock and key made for each other, unable to explain who made them. British biochemist Lawrence Henderson wrote about this in 1913 in a book with a simple title, The Fitness of the Environment. Henderson was a scientist of the old school, rigorous, methodical, far from philosophical speculation, and yet he arrived at a conclusion that still sounds provocative today. Water is so well suited to life that it cannot be considered a coincidence. He wasn't talking about God and wasn't building a conspiracy theory. He simply counted and found that the list of coincidences was too long. Let's go through it together. High heat capacity, necessary to stabilize the climate. High latent heat of evaporation, necessary for thermoregulation in living organisms. Ice that floats, necessary to preserve life in bodies of water through winter. Maximum density at 4 degrees, necessary to maintain liquid water beneath the ice. The ability to dissolve almost everything, necessary for water to carry nutrients inside cells and organisms. Molecular polarity, necessary for interaction with biological molecules. Surface tension, necessary for the capillary system of plants to function. Expansion upon freezing, necessary for breaking down rock and creating the soil in which plants grow. Not one of these properties is merely useful, each is critical. Change any single one, and the chain leading to life breaks. Astrophysicist Martin Rees, former president of the British Royal Society, calls coincidences like these fine-tuning. His colleagues debate what exactly this tuning means. Some say we live in one of a countless number of universes with different constants, and we simply got lucky to end up in the one where everything aligned. Others insist that life itself adapted to water, meaning water wasn't made for life, but life arose precisely because it found water and adapted to its properties. A third group asks a more radical question. Is life even possible without water at all? Theoretically, yes. Chemists consider liquid ammonia, liquid methane, and liquid nitrogen as possible alternative solvents for exotic biochemistry. On Titan, Saturn's moon, there are lakes of liquid methane. Perhaps slow chemical reactions are occurring there, capable over time of producing something resembling life. But everything we know about life is life in water. Every cell of every living creature on Earth, from a bacterium to a blue whale, functions only because it contains water. Water doesn't just fill the cell, it participates in protein folding, enzyme activity, and the transmission of signals between molecules. Remove the water and the molecular machinery of life stops. Not slows down, stops completely. Nobel Prize-winning biologist Albert Szent-Györgyi said it simply and precisely, life is water going about its business. Not carbon atoms, not proteins, not nucleic acids, water. All of those are important, but water is the medium without which they stop being alive and become merely chemistry. All of this raises a question even more fundamental than the question of water's fitness for life. Before water could become the foundation of life on Earth, it had to get here first. And that is far from an obvious story. Earth formed about 4.5 billion years ago from a rotating cloud of gas and dust around a young sun. In the zone where our planet took shape, it was hot. Very hot. Hot enough that most volatile substances, including water, simply evaporated and were blown away by the solar wind. By every calculation, the young Earth should have been dry, rocky, waterless. So where did the oceans come from? This is one of the most hotly debated questions in planetary science over the past several decades. There are several competing answers, and none has been accepted as definitive. The first, the comet hypothesis. Comets are essentially dirty snowballs, a mixture of ice, dust, and organic molecules. In the early era of the solar system, when the planets had just formed, there were significantly more comets and asteroids in space than today. They flew in wild, elongated orbits and regularly collided with planets. The period from roughly 4 billion to 3.5 billion years ago, geologists call the Late Heavy Bombardment, the time when the Moon received most of its craters and Earth received billions of tons of material from the outer solar system. If comets brought water, that would explain where so much of it came from. But here a chemical obstacle arises. Water differs depending on the ratio of ordinary to heavy hydrogen. Scientists measured this ratio in several comets and found it differs from Earth's. Halley's Comet, Comet Hale-Bopp, Comet Hyakutake, all of them contain water with roughly twice the proportion of heavy hydrogen as Earth's oceans. That's a chemical fingerprint. Water on Earth and water in these comets come from different places. There is, however, an exception. In 2011, the Herschel Space Observatory measured the composition of water in Comet Hartley 2 and found it matched Earth's. Comet Hartley 2 came from the Kuiper Belt, the outer edge of the solar system. This opened a new debate. Perhaps Earth's water was brought by comets from the Kuiper Belt rather than from the more distant Oort cloud. The second hypothesis, asteroids. Carbonaceous chondrites, a special class of rocky asteroids, contain significant amounts of water in a chemically bound form, embedded in the structure of minerals. Their isotopic composition of water is closer to Earth's than most comets. A series of meteorites of this type that fell to Earth and were studied in laboratories suggested that water could have arrived with them. The Japanese probe Hayabusa 2, which returned to Earth in 2020 with samples from the asteroid Ryugu, confirmed this. The samples contain organics and traces of water. Cosmic rocks hold water inside themselves, like small bottles with a message from the early solar system. The third hypothesis, internal. Perhaps water never escaped during Earth's formation. Perhaps it was originally embedded in the planet's rocks and then released through volcanic activity as steam, which gradually condensed into oceans. This hypothesis accounts for roughly a third of Earth's water. By some estimates, the rest came from outside. Most likely the truth is a combination of all three. Earth's oceans are assembled from different sources, some internal, mostly asteroidal, some cometary. Water collected here from across the solar system, pulled in by the planet from different corners of space. But this raises the next question. Where did the water itself form? Because asteroids and comets don't create water, they only transport it. Where does a molecule of 2 hydrogen atoms and 1 oxygen atom first appear? The answer is astonishing. Water is born in interstellar space, in cold molecular clouds, enormous accumulations of gas and dust scattered across the galaxy. Hydrogen and oxygen meet on the surfaces of dust grains and combine. Out there, it is almost absolute zero. Out there is a darkness that absorbs most forms of radiation. But even there, slow chemical reactions take place. Dust grains become coated with a crust of water and other molecules. Radio astronomers observe this directly. Water molecules are detectable in the radio wavelength range. Water is one of the most abundant molecules in interstellar space. When such a cloud contracts under gravity and forms a star with a planetary system, the water is already there. It arrives along with the raw material for the planets. In a sense, water is older than the solar system. The water molecules in your cells may have formed in a molecular cloud long before the sun ignited. Sitting with that thought, your head spins a little. Water is everywhere in the universe. Not a poetic metaphor, a statement of fact. Radio telescopes detect water vapor in the atmospheres of other stars. Spectroscopy reveals water in protoplanetary disks, young planetary systems still forming around recently ignited stars. The Cassini probe, studying Saturn's system, found that the moon Enceladus shoots geysers of water vapor into space. Beneath its icy surface lies a liquid ocean, probably warm near the bottom, where rock is heated by hydrothermal vents. Beneath the surface of Europa, Jupiter's moon, lies another sub-ice ocean, larger in volume than all of Earth's oceans combined. Probably salty, probably with an active geochemical cycle. In 2023, the James Webb Space Telescope detected water molecules in a protoplanetary disk around a star in the constellation Taurus, where planets are still forming. Water arrived there before solid bodies had even taken shape. In 2019, astronomers detected water in the atmosphere of the exoplanet K2-18b, a planet in the habitable zone of its star, about 110 light-years away from us. The first direct detection of water on a potentially habitable planet outside our solar system. Water is not unique to Earth. It is scattered across the universe the same way stars are. This leads to an uncomfortable conclusion. If water is a necessary condition for life, then life has a chance of existing in many places. Not guaranteed, but the odds are real and they are not negligible. In 2023, the James Webb Space Telescope detected in the atmosphere of the same exoplanet, K2-18b, a signal that some researchers connected with the molecule dimethyl sulfide, a compound produced on Earth only by living organisms in the ocean. This discovery triggered a heated debate in the scientific community. Some scientists consider the signal genuine, others point to possible artifacts in data processing and are calling for additional observations. For now, this is a weak and contested trace, not evidence. But the mere fact that we are searching and finding reasons to keep looking says a great deal. However, the further we look at water across the universe, the more clearly we understand something. Despite its ubiquity, we know surprisingly little about its nature. Not at the scale of galaxies, at the scale of a glass on a table. Here is an honest list of what science still cannot fully explain. First mystery, the structure of liquid water. There is no single accepted model of how water molecules are actually organized in their liquid state. Does water exist in two distinct states with different densities, as the hypothesis of Swedish researchers Anders Nilsson and Lars Pettersson proposes? Or is water a continuous network with no distinct structural states? Experiments yield different results depending on the measurement method. Ultrafast spectroscopy, neutron scattering, X-ray structure analysis, each method sees water slightly differently. Water is structured more complexly than any of our instruments can encompass in a single view. Second mystery, supercooled water. Pure water, free of impurities and container walls, can remain liquid at temperatures down to -40 degrees Celsius. This supercooled state is a zone scientists call no man's land. In this temperature range, water behaves in completely unpredictable ways. Its heat capacity, compressibility, and thermal expansion all change sharply. Experimenting in this zone is extremely difficult because the slightest disturbance, vibrations, dust particles, contact, instantly triggers crystallization. Water hides its deepest secrets precisely where it is hardest to reach. Third mystery, quantum effects. A proton, the nucleus of a hydrogen atom, is so light a particle that quantum effects in its behavior cannot be ignored. Protons in hydrogen bonds don't behave like classical balls on springs. They tunnel, passing through energy barriers without the energy expenditure that a classical object would require. Quantum tunneling of protons affects the rate of chemical reactions in water, including the biochemical reactions inside living cells. How strongly? Some scientists believe this partly explains the speed and precision of enzymatic reactions, an effect on the very foundation of life's biochemistry. There is no complete answer yet. Fourth mystery, the so-called fourth phase of water. Biologist Gerald Pollack from the University of Washington described a state of water near hydrophilic surfaces, proteins, membranes, gels, which according to his data differs substantially from ordinary liquid water. He calls it the exclusion zone and proposes that near any biological surface, water organizes itself into semi-crystalline layers with a different structure, different charge, and different chemical properties. This idea is contested, and the scientific community has not yet reached a consensus. But the very existence of the debate suggests that even water in the immediate vicinity of living cells behaves mysteriously. Fifth mystery, the superfluidity of water in nanotubes. When water is driven through carbon nanotubes with a diameter of a few nanometers, it flows hundreds to thousands of times faster than classical hydrodynamics predicts. Nanotubes of this size exist in biological systems, specifically proteins called aquaporins, discovered by Peter Agre, for which he received the Nobel Prize in Chemistry in 2003, pass water through cell membranes at extraordinary speed and with remarkable selectivity. How exactly this works at the molecular level is not fully explained. Water inside nanopores behaves differently from water in a glass. It switches into a special mode of movement. Sixth mystery, the paradox of isotope effects. Heavy water, discovered by Harold Urey, is chemically almost identical to ordinary water, but living organisms die in it with disturbing precision. Bacteria stop dividing, plants stop growing, mammals die if more than a quarter of their ordinary water is replaced with heavy water. Molecular processes in heavy water proceed more slowly because of deuterium's greater mass. But exactly how much more slowly, and why is that specifically critical for life? There is no precise answer. Life has turned out to be finely tuned to ordinary light hydrogen, and any deviation from it destroys a mechanism we don't yet fully understand. None of these are questions at the fringes of science in some remote corner of theoretical physics. These are questions about a substance you drink every day, a substance that makes up 60% of your body right now. We know a great deal about water, and that only highlights the depth of what we don't know. Perhaps that is the most honest definition of water that exists. Now come back to where we started. For 4,000 years, humanity considered water the most ordinary substance in the world, called it a primal element, then a simple compound, then decided everything about it was settled. Each time, it turned out not to be. Each time, water presented a new question we couldn't answer. We live on a planet coated in a substance whose anomalies created the conditions for our existence. It warmed the oceans and stabilized the climate. It preserved life beneath the ice through the harshest winters. It shattered rocks and created the soil in which plants grow. It gathered molecules from across the solar system, molecules that formed before the sun was born, and flooded a planet with them so that life became possible. Entering living cells, water didn't remain a passive filler. It joined the biochemistry and became part of the machinery. Every time you drink a glass of water, you are taking into yourself a substance older than our planet. A substance that has passed through interstellar clouds, tumbled through comets and asteroids for billions of years, and one that scientists have been studying for millennia and still cannot fully explain. You exist inside this mystery. It flows through your veins, makes up the greater part of every one of your cells, participates in every biochemical reaction you undergo. You are not outside the mystery looking in. You are made of it. Science never gives the feeling of completion, but sometimes, precisely when a subject seems studied down to its last molecule, it reveals a depth that makes you want to stop and simply look. Water is exactly that kind of subject. Ordinary, ubiquitous, seemingly dull at first glance, and at the same time the strangest, the most important, and the most unsolved substance we know. The next time you hold a glass of water and look through it at the light, pause for a moment. In that transparent ordinariness live more than 60 anomalies, billions of years of cosmic history, and questions that the finest minds on the planet have not yet answered. All of it within arm's reach.